Osmosis. You heard of a reverse osmosis water purification system? That's the osmosis we're talking about, except that's backwards. That's why they call it reverse osmosis. If you're more of a biology person, you might be familiar with osmosis. This is when a solvent moves from a less concentrated solution to a more concentrated solution. Here we've got an example. You may know that if you were to be stranded at sea, you're surrounded by an ocean of water, literally, but can you drink the ocean water? No. For one thing, it tastes nasty, right? Because it's so salty. But you'll actually become more dehydrated by drinking the salty water than you would if you didn't drink any water at all. And the reason is because of osmosis. So, here's an illustration of your intestine. Okay, so inside your body, let's see, am I backwards here? It's hard to figure out which direction we're going here. So if we drink salt water, this would be the inside of your intestine, which is actually the outside of your body if you think about it. And this is inside your body, on the outside of your intestine. There's a certain concentration of solute in the fluid in your body. Sodium chloride, potassium chloride, different ions. If you drink salt water, if you put a very salty solution into your intestines, it will actually pull water out of your body to dilute this. The way I think of it is, nature is trying to equalize things. And so here we have a less concentrated solution and a more concentrated solution. And it's trying to get them to be the same. The walls of your intestine are essentially a semipermeable membrane. They will allow some molecules to pass and not others. Water molecules are small and they can go through the membrane. The solute particles, for the most part, cannot. And so we can't have the salt molecules just moving over here. And so to equalize this, the water comes this way. And so it actually draws water out of your body and makes you more dehydrated than you were before. Here's an illustration of an osmosis cell. So if we take, this is the original U-tube. It's a U-shaped tube. It's a U-shaped tube, and it's got a semi-permeable membrane in here. It allows water to pass through, but not solute particles. And if we put a concentrated solution on this side and pure water on that side, what will happen is the water can go through the membrane. There's a lot more water on this side, and so water will go this way. There's less water here, and so less water will pass to the right. There is an equilibrium that will get set up here. But overall, the flow of water will be from the less concentrated to the more concentrated side. And so what we'll see is we'll actually see the liquid level rise up on the more concentrated side and go down on the less concentrated side. And the only reason that happens is the semi-permeable membrane and the difference in the concentrations. It's really kind of a cool phenomenon to see. If you want to stop it from doing this, you would have to apply a pressure here. We learned when we talked about gases that difference in liquid levels like this can be interpreted as a pressure. The difference here is what's called the osmotic pressure. If we want to reverse this process, do reverse osmosis, we need to add pressure here. We need to push. And that's what a reverse osmosis water purification system does, is it uses pressure to cause osmosis to go in the reverse direction, and so you get the pure water out and you're making this more concentrated. That's not a natural process. That's something you have to force. Osmotic pressure is also a colligative property. has to do with the number of solute particles in the solution. The more concentrated the solution, the greater the osmotic pressure. Osmotic pressure is something that they are concerned about in medicine because you don't want to give someone an IV solution that's either going to force water into their cells or pull water out. You want it to have the same osmotic pressure as the tissues. So you got to be careful with that. This is an illustration of what happens to red blood cells. Here we have normal red blood cells. They're kind of donut shaped. If you put red blood cells in pure water, inside the red blood cell is a certain concentration of solute. There's different substances dissolved in the water, and so the inside is more concentrated than the outside, and so water will flow into the cell, and it will cause the red blood cells to swell and eventually to burst. You obviously don't want that happening inside your body, right? But it does work well if you're trying to get blood stains out of clothing. If you soak it in cold water, the blood cells will burst, and then they wash out a lot easier. If you put red blood cells into a salt solution that is more concentrated than what's inside the cells, it pulls water out and causes them to shrivel up like this, which is also not very good. And so the terms they have for that are isotonic, iso meaning the same. It's a prefix that means the same. So this is isotonic. The concentration of the liquid outside the cells is the same as the inside. It doesn't matter what the substances are, but the molality has to be the same. Hypotonic, the surrounding fluid is lower in solute concentration. Hypo meaning below. Hypertonic, hyper is above. And so this is a hypertonic solution. It's more salty on the outside than it is on the inside. End of chapter 13. Pardon me?